Hi everyone, we are Team Paper JAMS from the Milwaukee School of Engineering. My name is Elena Janty,
I'm Jared Bluma.
I'm Max Mutza.
And I'm Stephen Peterson.
and this is a little bit about our project.
We began first by brainstorming different paper tower designs that would optimize each challenge. We also looked at different machines that are solely used to fold paper, shown here on the right. Using a decision matrix, we narrowed down our ideas to two different paper tower designs. The speed and height utilizes an overlapping feature held together by friction, while the strength tower features a cylindrical design, shown here on the right.
Now that we had these paper tower designs selected, we were able to test them to figure out what their limits were. For the strength tower, we were able to get a maximum load of approximately 1,500 pounds or 6.7 kilonewtons, having 100 sheets in a portrait orientation. For the height and speed tower design, we're able to get a height of approximately 15 feet before it would buckle. We then looked at ways that we could avoid adhesives but still hold the paper together. Here are shown a couple different stapleless stapler designs, and then on the right, you can see how we did some testing on that. Ultimately, we decided to go with a collar type design that avoided using these methods.
We then did some finite element analysis on an initial frame design, testing multiple materials to make sure it would withstand the loads being applied, and it was determined that it would not fail.
With our tower selected and initial testing complete, we then designed our initial robot components. The paper begins by entering the paper feed as shown on the left, and then is guided around a paper track using rollers. It's then guided around the shaft, whose cross-section is shown on the right, featuring a slit to secure the first sheet of paper. Once the paper is rolled around the shaft, the supporting donut then lifts using two linear actuators and the collar to support the tower, building from the bottom up. Also, for the strength tower, a bracket moves under the tower to support the added weight. The initial assembly is shown here, featuring the feed and track, as well as the linear actuators tight supporting the donut around the shaft.
We then did more FEA on a final, more compact wooden design, testing for strength and buckling. It was determined that it would not fail in either of these modes.
Through further testing and simulations, we decided to make some additions or some changes to the initial robot design. On the top left there, we have a combination of both the feed and the track mechanism to guide the paper onto the shaft, which we have the same cross-section shown on the top right. On the bottom left, you see the final donut lifting mechanism with the collar shown that I was talking about earlier, as well as extended arms on the side to give us more internal space. On the bottom right, we move towards a rack and pinion method to actuate that strength tower support.
Our robot utilizes two different roller types. The left roller helps keep the paper tight to the shaft, while the right roller is used for the strength and height tower specifically. It has one directional bearing to prevent the tower from falling down as the linear actuators go back down to the beginning position.
With our final design complete, we performed torque calculations to select electronic components to automate the tower building process. Our machine is controlled using an Arduino Mega microcontroller and 6 different buttons. Shown here is the wiring diagram for our control panel.
Here you can see two different isometric views of the full assembly minus that control panel and some of the electronics. Here are some pictures of the final robot that we manufactured. On the left and the middle, we have front and back views respectively, and then on the right, you can see that control panel that Elena was talking about, as well as some more electronics. Here you have a couple more zoomed in views. On the left, you can see how the paper is fed onto that track and feed and guided to the shaft for it to be wound. In the center, you can see the rollers that Jared was talking about. And then on the right, that's just showing that our robot does indeed fit within the 50 centimeter cubic box requirement of the competition.
With our robot assembled, we tested how it would perform in each challenge. For the height challenge, we were able to build a 4.6 meter tall tower in just under 6 minutes using 26 sheets of paper. For the speed challenge, we built our 1.5-meter tall tower in 2 minutes flat using only 9 sheets of paper. This speed challenge is similar to the elimination round, building our 1.5-meter tall tower in 2 minutes flat to lift the half-kilogram disc.
For the strength competition, a 73.5 centimeter tower was built using 80 sheets of paper in 8.4 minutes and was able to hold 183.7 kilograms. This gave us a score of 4,317 kilogram centimeters.
A special thank you to all of our sponsors and everybody that has made this competition possible. Thank you.